So the last talk will be presented by Fabian from Berkeley.
Thanks. So I'm going to speak about a method that we call adaptive free operator splitting, and this is joint work with Gauthier Gidel from Montreal University. So as my colleagues have already highlighted, the problem of minimizing a smooth trade-off between a smooth and a non-smooth term is ubiquitous in machine learning. And if the smooth term is simple enough that we have access to its proximal operator, then very efficient methods exist already, like proximal gradient descent. However, recently, the desire to encode more complex priors into our problem has led to the development of many other penalties that are more complex and for which we don't have access to its proximal operator. And examples of this are the group lasso with overlap, L1 trend filtering, total variation, isotonic constraints, etc. And now, a key observation of these penalties is that despite the fact that we might not have access to its proximal operator, many of these decompose as a sum of terms for which we do have access to its proximal operator. And this is true for all the examples that I highlighted before. And there's a rich literature on how to optimize this method, often referred to as proximal splitting methods, where we have classical methods like ADMM, or more modern ones like the Gondas-Vu algorithm or generalized forward-backward. And among this vast literature, I'm going to focus on one specific method that was recently proposed by Davis and Yin that's called the three-operator splitting. So the three-operator splitting can solve problems of this form, where I have a sum of three terms. The first term is smooth, and I have access to its proximal operator. And the other two can be potentially not smooth, non-smooth, but for which I have access to their proximal operator. First, it might be seen a bit limiting that I only allow for two proximal operators, but in fact, this is not a limitation, because once you have two proximal operators, you can very easily generalize it to an arbitrary number of them. Also, for simplicity in this talk, I will just focus in the formulation with two proximal operators. So how does this method look like? No need to memorize, but I'm putting it here just so you know what I'm talking about. So the method is very simple, fits in a single line. It iterates on a d-dimensional vector, and in the iteration requires to use the projection of the two terms and one evaluation of the gradient, and that's all. Now, as gradient descent, there are convergence guarantees for this method as long as the step size is strictly smaller than 2 over L, where L is the Lipschitz constant of the smooth term. But as for gradient descent, in practice, this result is often not very useful because there's often more than an order of magnitude difference between the step size that is allowed by the theory and the step size that performs well in practice. So here I run a very simple experiment using the three-operator splitting on a logistic regression plus overlapping group penalty, where I measure the convergence for different step size. The slowest one is the 1 over L, and then I keep increasing the step size until I get to 50 over L, which is the fastest converging line. So you can see that taking a much larger step size, you can converge much faster. So can we reconcile these two worlds? Or in practice, I can go fast by taking a big step size, but I lose the convergence guarantees. Is it possible to design a method for which I can prove that it converges, but it allows for a large step size? And the answer is yes, through a method that we call adaptive three-operator splitting, where the main idea is to not fix the step size in advance, but say, okay, we're gonna decide the step size at runtime based only on local information of the objective. And for this, we use a classical concept in machine learning, which is that of surrogate optimization. Instead of deciding the step size, the best step size for our objective, which can be very hard, what we do is to replace our objective by a quadratic surrogate and then choose the step size step size for that quadratic surrogate, which is a much easier problem. So in the algorithm, we start with an optimistic step size, which is typically the one worm we started from the previous iteration, and we check whether the quadratic surrogate that we constructed, which is a quadratic function that depends on the objective value and on the gradient, whether that quadratic surrogate is an upper bound on our objective function. And if that is true, then we can use that optimistic step size, where the influence on the step size is on the amplitude of that quadratic. And then the rest of the algorithm is the same as the three-operator splitting, but using that new step size. So as you can see, this is quite simple to implement. There's no need to have access to global constants of the objective, like the Lipschitz constant. Everything is decided based on local information of the objective. And the price to pay for this is that now you need to evaluate each time that you check this upper bound condition, it requires to perform 2 evaluations of the objective function. Although one of them is usually given as a byproduct of the gradient. But of course, the hope is that despite this slightly higher cost per iteration, the fact that you can take much larger step sizes is going to be beneficial in terms of runtime. So coming back to my first experiments, if here I choose the adaptive step size, how well does it perform? And it turns out that choosing the step size with the strategy that I just introduced, it often selects the step size close to the one that performs the best in practice. Now, it's nice to have a method that performs well in practice, but it's even better to have a method that performs well and for which you can prove convergence. So our second contribution is a new analysis for this method that also applies to the three-operator splitting. And so the analysis of the three-operator splitting is quite challenging, and one of the reasons for this is because the algorithm is not feasible. That is, at a given iteration, the objective function can blow up to infinity. So think that one of my proximal terms can be the identity function, and so at a given iterate, I'm not guaranteed to be bounded. And this is an issue because most proofs for gradient descent and proximal gradient descent rely on the fact that the objective function decreases. So this kind of proof techniques break for this method. So what we do is, instead of considering the objective function as a gap function to measure suboptimality, we chose instead to relax this objective function onto a saddle point problem. So using simple Fenchel duality, we transform the original problem into a saddle point problem where we're minimizing not over one variable, but over 2 variables. And this way, the objective functions that's in my saddle point problem has the nice property that now at the iterates, it becomes bounded. I no longer have the problem that it blows to infinity. And also because of Fenchel duality, I can recover my objective function by maximizing over one of the variables. And also the fact that I have a saddle point problem gives me a suboptimality criterion given by the definition of saddle point. That is that this expression is smaller than 0 only at a saddle point. So this already suggests what's going to be a good suboptimality criterion. And the kind of results that we have are basically the same ones that we can get for the non-adaptive variant, for the variant with a predefined step size, which is sublinear convergence for arbitrary convex functions. If on top of that we assume that one of the proximal terms is Lipschitz, so I can no longer blow to infinity, then we also have sublinear convergence on the objective values. And under additional assumptions, like strong convexity of the smooth term and smoothness of one of the proximal terms, we can also get linear convergence. Now, finally, we run several experiments on this method on many different problems that involve loss functions that are either logistic or least squares, and penalties that are either overlapping group Lasso, nearly isotonic, total variation, or L1 plus Tirage norm. And what we find out, so the adaptive operator, the method that we propose is in orange. So we found out that it often performs much better than the rest. We also see that in practice, it seems to have always a linear convergence rate, although the theory only predicts sublinear. And it's particularly efficient in cases of low regularization, which would be columns 1 and 3, and when the objective is logistic loss. So in these two plots, this would be the plots that have a least squares loss, where the method performs as good as the other. And that makes sense that the advantage is higher for losses that don't have a constant curvature, because if you have a constant curvature, then the advantage of adapting to the local information of the objective becomes less important. So it seems that this is more important in logistic regression. And that's all. If you have questions, please come to see me at poster 41.
So we have time for one question. So if you have a question, so if you have more than...
Thanks for the great talk. I think I misunderstood something, slide 4. Yeah. Your decrease condition isn't Q a majorizing function of f?
Sorry?
At condition 1, f
yeah.
of x plus, isn't Q a majorizing function of f?
Right. So it's guaranteed to be a majorizing function if you choose your step size small enough. So if your step size is smaller than 1 over L, then by the properties of L-smooth functions, it will minorize. This will be verified, right? So that gives you, for example, that this condition necessarily has a finite termination. It cannot run to infinity, for example. But the goal is, of course, to try to find step sizes, right, for which that are much larger than your potential 1 over L.
Okay, thank you very much.
Any more questions? So if not, let's... Oh.
You had a question?
My question is, So when we have more than 2 penalties, so when you evaluate in each iteration, do you need to evaluate a lot more function evaluations?
Right. So when you have more than 2 penalties, you can transform it into a problem with only 2 penalties by basically, as I have here, cloning the different variables and then adding a constraint of them to be equal. So in that case, what you're paying is that you're increasing the dimensionality of your problem. But it doesn't change the fact, it doesn't change your line search condition, because the line search condition only depends on your smooth term. It changes in the fact that now you need your vector of coefficients is larger.
Thanks. So thank you. So this concludes this session. So let's thank all the speakers again.